everyone. In this video I'm just going to do a quick recap of solubility product, and I'm going to look at some calculations. Now, first thing, when you think about solubility products, notice the word says solubility. We're really talking about the solubility of a salt in a particular solvent. It doesn't necessarily have to be water, but in a particular solvent. And most of the salts that are soluble in water, we know that the salts, all salts of sodium, potassium, and ammonium, those are all soluble in water. And then we have some insoluble ones, such as, for example, halogens, silver halides. Those would have been insoluble, classified as insoluble. But something to know is that many salts that we refer to as insoluble they actually dissolve in water to a smallest extent. So instead of saying insoluble at this level, we're going to say that it is sparingly soluble, meaning that it's partially soluble in water, right? Now, in a saturated solution of a sparingly soluble salt, equilibrium is established between the dissolved ions and the undissolved salt at the given temperature. Now, before I even explain this entire equilibrium part of it, we're gonna look at what saturated and supersaturated means. So it says in an unsaturated solution. In a saturated solution. Now, saturated means that we have the maximum amount of solute dissolved in a particular solvent. So, for example, you put a salt in a solvent, right? And all of that salt is dissolved in the solvent, right? So we have the maximum amount of that salt dissolved in the solvent. We say it's saturated, and no more can dissolve. Right, and when no more dissolves, we start to see a precipitate. We actually start to see crystals, and that's when we say that we have a supersaturated solution. Now, a supersaturated solution means that no more solute can dissolve in the solvent. We've exceeded all of the solubility. We can't dissolve any more solute in the solvent, and so we start to see crystals, right? And based on some experiments, you know that a salt can become more soluble if we increase the temperature, right? So if you increase the temperature of a supersaturated solution, you're going to have more solute being dissolved in the solvent, and so the crystals, they begin to disappear. That's if you increase the temperature. Now, for unsaturated, it would have been the opposite. In unsaturated solution, you can actually have more solute being dissolved in the solvent, right? So you're not seeing the crystal. You're adding the crystal and you're not seeing it. It's all being dissolved, right? So that's for unsaturated. More solute can actually be dissolved in the solvent. Now, going back up here, it says in a saturated solution of a sparingly soluble salt, sparingly meaning partially soluble salt, equilibrium is established between the dissolved ions and the undissolved salts at a given temperature. So what it's saying is that even if we have a sparingly soluble salt, we can have an equilibrium being reached between the dissolved ions of that salt and also the salt itself. Alright, so for example, barium sulfate, remember that all sulfates are soluble except those of sodium, potassium, and ammonium, and also you have barium sulfate, which is partially soluble. Right, so barium sulfate, it's partially soluble, however we still use the state symbol solid, partially soluble. Not all of it will dissolve in the solvent. And at equilibrium we have similar concentrations of the salt and also the ions present, the same concentration of the salt and the ions present, right? So note that even though it is sparingly soluble, right, let me just say this, if it was a insoluble salt, completely insoluble, you would not have any ions at all, right? But since it's sparingly soluble, we can have some ions being produced at equilibrium, right? Now note that at equilibrium we have the rate that we form the ions being equal to the rate that we form the solid. So let me say it again. At equilibrium, the rate that we form the ions is equal to the rate that we form the solid salt. Alright, so that's the equilibrium expression, and for solubility products we say that this equilibrium expression is called KSP for solubility product. Alright, Um, Now, if we were to write this as Kc, our equilibrium constant, is going to be, note we have our products here on the right hand side over reactant. So that's why we have our product over reactant. Note that if we had coefficients in front, those would be used as the powers for our concentrations right here. Right, so Kc is equal to barium 2 plus, the concentration of barium 2 plus, multiplied by the concentration of the sulfate ions, divided by the barium sulfate. Remember, it's product over reactants. Right? Now this is saying that cross multiplying gives us Kc multiplied by barium sulfate, the solid, is equal to the barium and the sulfate ions. This is how we get our new solubility product expression. Right? So instead of having the constant, right, it now becomes the Ksp, which is the solubility product of barium sulfate, of the salt. Right? Note that it says the solubility product, which is Ksp of barium sulfate at 25 degrees Celsius, is the product of the concentration of the barium and the sulfate ions in the saturated solution. Right, that is what Ksp is. It's a product of the concentration of the ions in the saturated solution. Right, I already explained these. Moving on. Right, so moving on, we have the unit for solubility being grams per 100 grams of water. Right, you would have been exposed to this in grade 9, but this is a general unit. If this grams right here represents the mass of the solute, this right here represents the mass of the solvent. So if it were, let's say, 38 grams of barium sulfate that is able to dissolve in 200 grams of water at RTP. So that is how the unit would look. 38 grams per 200 grams of water at RTP. Right? Now, I'm gonna go through the term saturated KCl solution, and then sparingly soluble calcium hydroxide and an insoluble silver chloride. And we're going to use back our terms saturated, unsaturated, and supersaturated if needs be. Right? So for saturated KCl solution, remember saturated means that we have the maximum amount of solute dissolved in the solvent. Right? So in this case, we won't be seeing any crystals. We won't see any crystals. Since all the crystals would have been dissolved, right, we won't see any crystals at all. Now this is saying that at the temperature is not given, but the maximum amount of potassium chloride that dissolves in water at a particular temperature would have been 35.9 grams. Right, and as we say, no crystals are seen, and this is the unit, 35.9 grams per 100 grams of water. Right, that's this if we have a saturated solution of KCl. It would become supersaturated if we added more grams of KCl. Right, we start to see crystals if we add more grams of KCl in this mass of water. Right, note that solubility also increases as we increase the volume of the solvent, and solubility increases as we increase the temperature of the entire solution. Alright, so for calcium hydroxide, we have sparingly soluble here, which means partially soluble, of course. The maximum, know the difference in the mass, the maximum amount of calcium hydroxide that can actually be dissolved in water at a particular temperature is 0.133 grams. Alright, so the unit 0.133 grams per 100 grams of water. That would have been the solubility of calcium hydroxide. For silver chloride, we know that this is completely insoluble. However, we still do have a small amount of silver chloride that is dissolved, even if it's cold silver chloride. Remember that hot silver chloride is soluble, but cold is insoluble. Even though this says it's insoluble, know that you still have a small amount of ions that are able to dissolve in the water. Notice the mass, 0.00019 grams per 100 grams of water. Right, so you're gonna actually see a lot of crystals in this case. Yes, especially if we add 1 gram of silver chloride, you're gonna see a lot of crystals. Alright, now the solubility product is the product of the concentration of each ion in a saturated solution of a sparingly soluble salt at 298 Kelvin raised to the power of their concentrations, which we went over already. This is just showing us how we can actually determine or write the KSP. Right, remember KSP is not product concentration of products over reactants. Instead, KSP is simply the equivalent to the ions present, the ions that the sparingly soluble salt would give us. Right, so for example, we have our cobalt hydroxide. Note that right here we have 1 cobalt and we have 2 hydroxide ions. The fact that we have 2 of these, we're gonna raise it to a power of 2. Gonna raise it to a power of 2 here, and it's only 1 cobalt, so it's just gonna be to a power of 1. Right, therefore this is how the KSP equation looks. Remember, KSP is equal to the ions in the saturated solution of a sparingly soluble salt. Right, so this is the KSP of cobalt hydroxide. The KSP of aluminum oxide, we have 2 aluminums, 3 oxygens, so KSP is equal to Al3 plus raised to the power of 2 multiplied by O2 minus raised to the power of 3. Whenever you're writing your KSP expressions, please use your ions, right? Make sure that you write your ions, because remember, KSP deals with ions. So be sure that you write your ions and also write the power that it's raised to. The power is equal to the amount of that atom, or the amount of that polyatomic ion. Let me use the word ion. The amount of the polyatomic ion or the monoatomic ion that is present. Alright, so sometimes we do have to solve for the units of KSP, and this is an example. So we have the KSP is equal to the cobalt ion multiplied by the hydroxide ion. It's KSP also deals with concentration. Note the square brackets. So right here is mole per dm cube times mole per dm cube squared. Right, so it's therefore going to be mole per dm cube times mole squared. So remember, when you have your brackets, it's going to be 1 times 2, and it's going to be 3 times 2, which gives us 6. Right, now when you're actually multiplying powers, when you see the multiplication here, instead of multiplying the powers, you're going to add them. So this becomes mole, this would have been mole to the first power. 1 plus 2 give us 3, and 3 plus 6 give us 9. So this is the correct unit if you're solving for the unit of KSP. So it can be written as mole cube per dm to the 9th, or something like this. Same thing. Right, note that I did not use I have a negative sign here because it's per, and I don't have the negative sign for the power here. Now we're looking at the calculations, which I'm just going to go through very quickly, because we don't have it's not that many calculations to look at. So for the calculations, we're really looking at how to calculate KSP and how to calculate solubility, and then we get into the common ion effect. Right, so this question says a saturated solution of lead iodide contains 0.07 grams of lead iodide in 100 grams solution. Calculate KSP. Alright, so we need to solve for KSP, and we don't know the concentration of any of the ions in lead iodide. Right, only thing we know for lead iodide is that we know the mass of lead iodide and we know the molar mass. Right, once again, we do not know the concentration of any of the ions in lead iodide. I should have actually written out my KSP for lead iodide, so let us write it. KSP is going to be equal to PB bracket 2 plus, it's only 1 lead. Once again, iodine, we have 2 iodine, charge of iodine is 1 minus. Alright, so that would have been our KSP. Once again, we don't know the concentration of any of these ions. So what we can actually calculate is that we can calculate the concentration of the lead iodide, which is the salt. Right, now if you want to calculate the concentration of something, you need 2 things. You need to know the mole and you need to know the volume. Remember, mole concentration equal mole over volume, right? So as I have here, it's going to be mole concentration equal mole over volume. To solve for mole, we're going to use the mass, which we're given here, the mass of the potassium iodide divided by the molar mass of the potassium iodide, and this gives us 0.0000, I think I said that too much, but 0.000165 mole. And as for the volume, right, if you know, based on the density of water, which is 1 gram per centimeters cube, when we convert this is also saying that 1 gram is equal to 1 centimeters cube. So if the mass of the solution is 100 grams, 100 grams is also equal to 100 ml, and 100 ml is also equal to 100 centimeters cube. But remember that whenever you're solving for the volume, you have to convert centimeters cube to dm cube. So it becomes 0.1 dm cube. How we got this? It's 100 centimeters cube divided by 1,000. Right, that's how you convert to dm cube, and you will get 0.1 dm cube. Now we work out the mole concentration. Right, we put the mole that we got divided by the volume. Right, and therefore our solubility concentration of one of the ions is equal to 1.65 times 10 to the minus 3 mole per dm cube. Right, now we need to determine the concentration of each ion, and something to know is that the concentration of the salt is equal to the concentration of one of the ions. So let me say it again, the concentration of the salt is equal to the concentration of one of the ions. So when we put in our KSP equation, now we have KSP is equal to lead 2 plus and our iodine 1 minus raised to the power of 2. Right? Once again, if the solubility concentration of the salt is this, then therefore lead 2 plus is going to be equal to this, and iodine 1 minus is also going to be equal to the same concentration. Right? We don't divide anything, we don't split it in two. No, all we do is that, as I said, if the solubility concentration of the salt is equal to X, therefore the solubility concentration of one of the ions is also equal to X. And we just put it into our brackets and we put back the square at the top and we solve. Note, I also, when we square it, it has an effect on the unit, so it becomes mole squared, right? Mole, if it's mole concentration raised to the power of 1, is going to be, since we're multiplying units, the powers are going to be added, so it's going to be 1 plus 2 give us mole cube. Right, we would have worked this already, multiplied, then you get this answer. And if I were to just write this out as mole per dm cube, it now becomes mole cube per dm to the minus 9. This should actually not be here, it should be a dot. Alright, so I hope that was straightforward. We're gonna have to work one together. Alright. So for this one, so for this one, it says a saturated solution of barium fluoride contains 0.138 grams of barium fluoride in 200 grams of the solution. So this is the mass of the solution, this is the molar mass of barium fluoride, and the mass of barium fluoride. Once again, I'm going to write my KSP expression first for barium fluoride, which is going to be KSP is equal to BA, barium is 2 plus, and it's only one barium, so it's going to be raised to the power of 1. Fluorine is 1 minus, we have 2 fluorines. So that's our KSP expression. Now what we need to do next, now it says we need to, a saturated solution of barium fluoride contains 0. That it doesn't say specifically, but I'm sure we need to also determine KSP. We need to calculate KSP. Alright. Now, when we're calculating KSP, remember KSP is also like the concentration of the salt, right? That's why we did all of this right here. All of this right here, KSP would have been the concentration of the salt. Alright, so that's what we're solving for. But we can't solve, we We don't know the concentration of the salt. The only thing that we know is the mass and the molar mass. Now from equation, concentration equal mole over volume. Alright, concentration equal mole over volume. To solve for mole, mole is equal to mass over molar mass. Mole equal mass over molar mass. So it's going to be 0.138 grams over 1753 grams per mole. Let me just work this out. And so I get, I'm just gonna write this as is 7.87 times 10 to the minus 4, and since it's concentration, mole per dm cube. So we would have gotten the concentration of the salt, but we need to solve for the KSP of the salt. Remember, KSP is equal to these ions here, right? And if the concentration of the salt is this, therefore the concentration of one of the ion is also this. So it's going to be KSP is equal to 7.87 times 10 to the minus 4 mole per dm cube raised to the power of 1. I'm just writing the 1 so you have an idea. You don't need to write it. In chemistry we call it the invisible one, so you don't need to write it. Then we do, I'm losing the train of thought, but we do 7 point, yeah, so this is where we're at now. It's 7 times 10 to the minus 4 mole per dm cube squared, right? And so now it would be I believe it's going to be 7.87 times 10 to the negative 4 cube, but we can work it another way. I'm just going to write back 7.87 times 10 to the minus 4 mole per dm cube times, so this is going to be squared 6.197 times 10 to the minus 7 mole squared. So remember to square the units as well. Mole squared, 3 times 2 give us 6 dm 6. Alright, and this is going to be multiplied by 7. Let me just put a bracket. 7.87 times 10 to the minus 4. Alright, let me do it this way because I believe it can also be cubed. So 7.87 times 10 to the minus 4. Okay, cube. So it's gonna be 1, 2, 3, 4, 5. 4.17 times 10 to the minus 5. Let me know if my answer is correct, of course, because I'm doing it another way. So you can work it out this way. Let me know if my answer is correct, but this is the correct format of working it out. The units now, since it's multiplication, we're just going to add the units at the top. So it's mole 1 to the 1 to the first power plus 2. So it's going to be mole cubed per 3 plus 6 equals 9 dm to the 9th power. Right? Alright, so let's look at another question. So that's how we determine the KSP. Now remember, KSP, first you solve for your concentration of the salt, then you use the concentration of the salt, put it in where you would have the concentration of the ions, solve all of that, then you get your KSP. Now what if we needed to determine the solubility, not KSP? KSP is the solubility product of the ions, but we needed to determine the solubility of the salt itself. Alright, so this says calculate the solubility in mole per dm cube of copper sulfate if KSP equals 2 times 10 to the minus 5 mole squared per dm to the minus 6. It's almost like working backwards. Right, we're calculating the solubility of copper sulfate if we have this value as KSP. Now, note here that this is how the solubility product is going to look for copper sulfate. You see, copper sulfate is actually calcium sulfate. You understand my handwriting. So we have calcium sulfate. When we write the KSP of calcium sulfate, it becomes Ca2 plus to the first power. Put your brackets. SO4 2 minus to the first power. We don't have any brackets here, so it's fine. Now how I work this out, it's my simple way of doing it. Right now, what we're going to do is that since this is the value of KSP, right, since this is the value of KSP, we're going to combine this expression right here. So it's almost like I write ion right here, but you can write X for ion. Alright, so we're gonna combine this expression right here. So it would actually be ion to the second power, ion squared. 1 plus 1 gives us 2, so ion squared. So KSP is equal to ion squared. Alright, so it says that solubility concentration of the two ions, that is what it's saying, and we're just making ion the subject. That's what we're doing right now. We're going to solve, we're going to transpose to make ion the subject. So to get rid of the squared, we're going to have to put a square root, that those would cancel, and we put the square root over this side. So therefore it's going to be the square root of KSP is equal to ion. Alright, we need to determine the solubility of the ion. Even though it says calculate the solubility in mole per dm cube of calcium sulfate, how we calculate the solubility is that you have to calculate the solubility of the ion itself. Right? Remember that each ion has their solubility in KSP. Right? So this is the ion. Let's say we're looking at the solubility of calcium in KSP, solubility of sulfate in KSP. So we're solving for these, the concentration, the solubility concentration of the ion. So this is where we're at in our calculation. So we have KSP, the square root of KSP equal ion. So we put in our value. This was what KSP is equal to, equal ion, and when we square root it, we get this as our answer. So once again, if you need to calculate the solubility and you're given KSP, you write out your solubility equation. You write out your KSP equation, and then you use KSP to solve for the solubility of the ion. Right? And you're going to make the ion subject. You're going to make the ion the subject. So this could have actually been KSP equal ion to the first power and ion to the first power. So all I did was simplify to make ion the subject right here. In this case, it would have been ion to the squared, or to the second power. Right? So once again, you solve for ion, you're solving for the solubility of this ion here using KSP. Alright, this is another question. So it says if the KSP of silver carbonate at and this is a silver 1 carbonate at 20 degrees is 8 times 10 to the 12 mole cube per dm to the 9th power. Calculate the solubility of silver carbonate. So for the solubility, remember for solubility you use KSP. You're given the KSP, so you just need to find the solubility of any one of the ion. We're going to make the ion the subject as a matter of fact. So this is our KSP expression. KSP is equal to silver to the second power. We have 2 silvers, and then we have carbonate to the first power. It's only 1 carbonate right here, and it becomes KSP equal ion to the second power and ion to the first power. You're gonna simplify to make ion, just you have 1 ion on this side, so it's going to be KSP equal square bracket ion. When you have your brackets, or when you're multiplying, you add the power, so 2 plus 1 gives us 3. And that's what we get for KSP here. Remember that we're making ion the subject. When you're solving for solubility, you solve for the ion, the solubility of the ion, not the solubility of the salt, but the solubility of the ion. So this is going to be, to get rid of this, we're going to do a cube root to get rid of the cube root to get rid of the cube. Whatever you do to one side, you do to the other. So it's also going to be cube root of the KSP value. Alright, cube root of the KSP value. And when we do that, this is the answer that we get for the ion solubility, any one of the ion solubility. And this is the solubility of one single ion. Alright, so the solubility of Ag2 silver carbonate equal this at 20 degrees Celsius. Alright, once again, whenever you're solving for the solubility, you solve for the solubility of the ion. Even though it says that you're solving for the solubility of the salt, it's really just the ion solubility you're solving for. Now this one we get to do together. You can pause the video and try it on your own. So it's going to be, if the KSP of barium fluoride is 4 times 10 to the minus 4 mole per dm cube, what is the solubility of barium fluoride at 30 degrees Celsius? Alright, so once again, if you're solving for solubility of a salt, remember it's really the solubility of the ion. So I'm going to write my KSP. KSP is equal to barium and fluorine. Barium has a 2 plus charge. My bracket, it's only 1 barium. And fluorine has a 1 minus charge. We have 2 fluorines right here. Remember that we're solving for the solubility of the ion. So we're going to make ion the subject. It's going to be KSP equal square bracket ion 1 square bracket ion raised to the power of 2. I'm going to simplify this even further. KSP ion 1 plus 2 is going to give us 3, right? And now we put in our values. So KSP of barium fluoride would have been 4 times 10 to the minus 4 mole per dm cube. I believe the unit of this should have been mole cube per dm to the 9th power. Right, so it's going to be equal ion concentration. To get rid of the cube, you have to do a cube root. Do the same thing over this side. And so our answer is going to be 4 times 10 to the minus 4. So I got 0.0736 mole per, so this would have been 3 and 9. If you cube root this, 3 divided by 3 goes 1, 9 divided by 3 goes 3. So we get dm cube is equal to ion. So this is the solubility of, this value is the solubility of barium fluoride. Yes, remember that if you're solving for the solubility of a salt, you use actually technically are solving for the solubility of the ion. This is another question. If the solubility of silver chloride at 18 degrees is 1 times 10 to the negative fifth mole per dm cube, this is solubility. Calculate the value for KSP at this temperature. I say once again, you can pause the video and try to solve on your own. So in this case, if the solubility of silver chloride at 18 degrees is that, right, we're solving for KSP. Now KSP is equal to, I'm gonna write the solubility product, silver. Note that in this case silver has a 1 plus charge, and Cl 1 minus. Right? That's our equation. We're solving for the solubility of silver chloride. I believe the units are wrong though, but let us work with it and see where we get. So in this case, what's next? We have our solubility product and we need to actually solve for the solubility. Now we're going to simplify, so it's going to be KSP is equal to ion raised to the value of KSP is 1 times 10 to the minus 5 is equal to ion raised to the power of 2. To get rid of the 2, you do a square root. Do the same thing over this side. And let me just work it very quickly. So square root of 1 times 10 to the negative 5 power. Answer is 3.16 times 10 to the negative 3 equal the ion, which as I say would have been the solubility of AgCl solid. That's our answer there. Now I'm looking at the common ion effect. I'm trying to get this video done as quickly as possible. Now I'm looking at the common ion effect. Alright, now for the common ion effect, where we have a KSP, KSP is used to predict whether a precipitate is formed when two solutions are mixed. Alright, so before we even look at the common ion effect, we're going to look at predicting if a precipitate is formed. And when you're predicting if a precipitate is formed, you need to know two things. You need to know about KSP, and you also need to know about the ionic product. Right? Now in this equation, we have barium chloride plus sodium sulfate. This is a double displacement reaction, so we're going to form barium sulfate plus sodium chloride. As we know, if the salt contains sodium, potassium, or ammonium, it is soluble. And this is actually an ionic precipitation method. Usually for ionic precipitation, you form a soluble salt and an insoluble salt. But at this level, we don't say insoluble, so it would be a partially soluble or a sparingly soluble salt. Right, so sodium chloride being our soluble salt and barium sulfate would be our sparingly soluble salts. All sulfates are insoluble except, you know, the common ones: sodium, potassium, and ammonium, and barium is sparingly soluble right here. Now, so it says specifically for barium sulfate, this, even before I look at this, because this might be a little confusing for you. So let's look at what ionic product is. So we know what KSP is. Alright, we know what KSP is. Ionic product is the product of the concentration of any of the ions. It's the product of the concentration of any of the ions. Right? Basically, it's just the concentration of the ions that are there. Alright, that's it. Now, if for a precipitate to form, you need to know what the ionic product is and also what the solubility product is. Remember, the solubility product is the concentration of the ions when we have a saturated solution of that sparingly soluble salt. Right? So in this case, ionic product and solubility product. Solubility product, the solubility of the ion in a saturated solution. Right? Solubility of the salt in a saturated solution. And then ionic product now would have been the product of the concentration of any of the ions. Alright, now in this case, Q is for ionic product. If Q is less than KSP, we have more salt can be dissolved. Right? Remember that KSP is solubility. So if you have the solubility product being greater, it deals with the solubility of our salt. If the solubility product of the ion is greater than Q, therefore more salt can be dissolved. Right? More ions are soluble and we won't see a precipitate. Now if Q, which is the ionic product, which is the product of the concentration of any ion, and just so I can put this into perspective, it just came to me, so I'm just gonna go through it. So it says the product of the concentration of any ion. So it's going to be the concentration of our ion, should have written it different, Na plus Cl, concentration of the ions, the product of the concentration of the ions, right? So this right here would have been the product. This is the product of the concentration of the ions, the salt. That's what it's referring to. So if the ionic product, which we're therefore getting the salt. If the ionic product is greater than the solubility product, which refers to the solubility of the salt, which gives us the ions, therefore we're going to have a precipitate being formed. Remember that for ionic product, we're getting the salt, while for solubility product, we're actually getting the ion. Alright, so if the ionic product is greater than the solubility product, we're going to see a precipitate. If they're equal, then the solubility is just saturated. The solution is saturated. If Q is equal to KSP, the solution is just saturated. You would have the maximum amount of solute dissolving the solvent. You have very similar amount of ions and salt present. Now for the calculation, it's a bit different from almost done. Alright, for the calculations, you have will a precipitate form when 6.0 times 10 to the negative 5 mole per dm cube barium chloride is added to this. And you know what? On that note, I'm going to stick a pin. Join me on the other video.